So once you collected your experimental small angle scattering data from the solutions of your particles of interest, you end up with a collection of two-dimensional images. And the first data processing step is to average the isotropic scattering patterns into one-dimensional experimental data sets and to subtract the background. So, and you can do this and many more data processing and analysis steps with programs from the ATSYS package. And I will give you a very brief overview of what you can actually do with the ATSYS software. My favorite data analysis approach is basically when you have a model of whatever particle you are studying. And if you have a model, you can actually compute the scattering from this model and compare it to the experimental data. And you can also do some modeling, atomistic modeling, for example, by changing this model and in the hope that another model will fit your experimental data. When I say model, I don't mean the actual single model. The model can be quite complex. For example, it could be a mixture of different models, different states of the protein. It could be a pool of flexible proteins, and it could be other ways of accounting for polydispersity of the sample. If you do not have a model, you can still evaluate a number of parameters directly from the experimental small angle scattering data set, and you can actually reconstruct the ab initio shape of the particle of interest. So you can make an ab initio model, which is typically a collection of small beads that are put together in a shape, the scattering of which fits the experimental data. So all of this you can do with various programs from the ATSYS software package. This package is around since 2 decades. It has always been the most popular software package if you work with biological small angle scattering data. It consists of about 100 programs. Some of these programs have a graphical user interface, others are command line programs, which are great if you want to automate your data processing flow. And we also have a PyMol plugin. This all comes as a single package, which is compiled for Windows, various versions of Linux, and for Mac. You can even use ATSYS programs without installing it on your computer. You can use the ATSYS online web portal where you can submit your experimental data and your models to be processed and on the EMBL cluster. We have various commercial licenses for our industrial users, and we also have academic licenses for users from nonprofit organizations which enjoy using of ATSYS free of charge. I actually made a video where I go over 30 most popular ATSYS programs in 24 minutes. There I go over primary data analysis steps, ab initio modeling, and modeling of monodispersed systems and polydispersed systems. I encourage you to watch this video if you haven't done so yet. So today I will tell you about processing of data which I downloaded from the small angle scattering biological data bank. This data set consists of about 3,000 radially averaged data frames which come from size exclusion coupled SAX runs from the P12 beamline. So, and if you work with this kind of data, you need to have like a quick overview of it to understand what is going on there. And the easiest is to load this data in the program called Chromix. And once you load this data, it will be very quickly processed into a kind of illusion profile. And what you see now is the scattering intensity from a small angle range of each frame, plotted frame by frame. And it immediately tells you a lot about your sample. For example, one can see that the background is fairly stable and that this was a monodispersed solution. So if you work with SAX data, I encourage you to get familiar with the Chromix program. It can actually do much more than I will be telling you today. And also, if you work with data which are in inverse nanometers, I encourage you to go to the settings and override the default angular range which is used for plotting. All right, once you loaded your data, you can click the sample automatic selection button, and the program will find all the peaks and will select the first peak. And once the first peak is selected, you can actually automatically find the best matching buffer. Of course, you can adjust this or select the sample region or the buffer region manually. And once you are happy with the selected peak and the selected frames, which are your background, you can click the button Process Selection. What will happen then is that the background frames will be subtracted individually from the peak frames, and the subtracted data will be scaled for concentration, averaged, and loaded to the program called Primus. This is a program for interactive primary data processing. So today I will show you how you can analyze your data using DAMIF wizard and using programs Chrysal and sReflex from Primus. So we will start with Ab Initio wizard. If you click the button DAMIF, it will start the so-called shape wizard, where you can go through the data analysis and reduction steps, which are necessary if you want to reconstruct your shape Ab Initio. So the first step is, as always, the Guinier analysis. So here on the left-hand side, you will see the Guinier plot of the small angle portion of your data, and you can estimate how linear your Guinier region is. In the middle section, you will see the dimensionless Kratky plot of your data, and on the right-hand side, you will see a number of parameters, including the radius of gyration estimated from this Guinier approximation. And of course, you can change the angular range, which is used for the Guinier region. And you can play with that until you think that the Guinier fit is linear and there are no deviations. And then you can click Next. This will bring you to the next data processing step, which is the pair distance distribution function evaluation. In the middle section of the screen, you will see the actual pair distance distribution function, which will be automatically computed for you without any input needed. And on the left-hand side, you will see the fit of the Fourier transform of this pair distance distribution function to your experimental data. And on the right-hand side, you will again see a number of parameters estimated from this pair distance distribution function, and a number of parameters that you can actually vary. For example, the Dmax, the maximum intraparticle distance present in your particle. So you can decrease the Dmax and see what effect it will have onto the fit to the experimental data, or you can increase the Dmax to have a better feeling what kind of maximum distance is present within your particle. So it appears that the initial guess of 5.1 nanometers was actually quite good. So what else you can do here? You can vary the alpha parameter. So you can increase the alpha to get a smoother pair distance distribution function. However, higher alpha values mean that the fit to the experimental data will be less precise. So you can decrease the alpha parameter to get better fit to the experimental data, but with smaller alpha values, the POFR function will be not that smooth. So you need to find the balance or rely on the automatically estimated alpha parameter. So once you're done with that and happy with the alpha and the fit to the experimental data and the Dmax, you can click Next. And this will bring you to the window where you configure how to start the DAMIF runs. So DAMIF is a Ab Initio shape reconstruction program. Here you can choose between fast mode and slow mode. Fast mode is a preset that results in bigger beads and smaller number of bigger beads. And slow means that will be a larger amount of smaller beads. So you can repeat DAMIF. You can start it, run it several times and average multiple models with a program called Damaver, and then refine the average model with a program dummy. This totally helps in certain ab initio reconstruction cases to achieve a better fit to the experimental data. So you can choose between symmetry if you know that you have a symmetric particle, and you can also specify an anisometry if you work with flat particles, or if you know that your particle is prolate, is elongated. And of course, you can specify the angular scale of your experimental data. If you don't do so, the program will guess the units of the experimental data for you. And then we can click commit. We will see some command line output of the programs that are running in the background. And once they are finished, you will see a fit to your experimental data. It is very important in any case of modeling that you have a model that actually fits your experimental data, or is at least as close to your experimental data as it gets. So this is pretty much a perfect fit. In the bottom of this window, you will see 3 tests applied to the fit, and you will see that they are all in the green area. That means that this fit is as good as it gets. All right, so let us have a look at the model that we have reconstructed. For that, we will open the working directory and load the model into PyMol. I recommend you use show spheres in PyMol if you want to have a look at your ab initio reconstructions. All right, let's have a quick look at the program Chrysal. The idea of Chrysal is to compute the scattering from a given PDB model and to fit it into the experimental data. So once you selected your model, you can configure Chrysal, and there is a number of options. Of course, you can provide the experimental units of your data. If you don't do so, Chrysal will guess the units from the angular range. You can specify the number of points on which Chrysal internally will compute the scattering of your model, and the number of spherical harmonics. So the more spherical harmonics Chrysal will be using, the more accurate the scattering will be computed. However, the slower the program will be. And I almost always check the apply constant subtraction checkbox, which will allow Chrysal to correct the background at higher angles. So, and we will look into the S-reflex options in a minute. So if we click commit, it will again bring us to some command line outputs, and then eventually within a few seconds, we will see processing complete, and we will get another fit. So this will be the fit of your atomic model to your experimental data. So what does this fit tell us? This fit tells us that size is correct, but the overall scattering from this model follows the experimental data, but it doesn't fit it quite there yet. So you will see that the correlation map test is in yellow and the other two are in red. That means that there is room for improvement. You can actually modify your model such that it fits the experimental data better. So, but let us first compare the models that we just used with the ab initio reconstruction. To do that, we can load both models to PyMol, but as you can see, they don't overlap very well. And instead of manually dragging one model on top of the other, you can use the PyMol plugin called SASPy, which comes with the ADSAS package. And in this plugin, you can choose the program called SuPalm. And this program will superimpose 2 models one on top of the other. So it is not possible to do that using the functionality of PyMol. PyMol can align only models which have partially overlapping sequences. So, but in SuPalm, you can just first choose the model which should be the template, then choose the model to be aligned, and click the execute button, and then one model will be rotated and shifted such that it overlaps best with your template model. So as you can see, it's hard to figure out how exactly do they overlap. And to improve this display, you can click the Dumb Display tab in the SASPy plugin and choose the color and level of transparency and the model which you want to modify, and then you just click the execute button. And voila, you have the ab initio model half transparent, and this is much better to look at models if you happened to want to compare the ab initio model with your atomistic model. And very few words about sReflex. sReflex is a program which can apply normal mode refinement to the given protein model. So effectively, it will try to refold your protein. So as you probably know, proteins in solution may undergo conformational changes, and they may not look exactly like they look in the crystal structure. So these two models, for example, produce dramatically different scattering patterns. What sReflex will do for you, it will start from the given model, and it will try to flexibly bend it such that it fits the experimental data better.